Hello, we're the Community Science Traffic Counter, Team 1. My name is Hetul. I worked on this project alongside Rucha, Tobi, and Chengxuan. Our client and sponsor for this project was Sandra from the Tomorrow Foundation, which is an Edmonton environmental charity. Currently, the Tomorrow Foundation is collecting air quality data at certain community locations, and they'd like to add further context to this data by gathering traffic data at the same location. So previously, the Tomorrow Foundation developed a prototype which used machine learning to gather this traffic data. However, the prototype was extremely difficult for community members to use, as well as it had some technical and software issues, thus rendering the prototype essentially ineffective. Therefore, throughout the last few months, our team designed an affordable traffic counter that can be installed and maintained by community members with limited technical expertise. We also developed our own project-specific software using open source resources. The counter is able to distinguish, detect, and track different vehicles passing a particular area, as well as update those results to a database. Finally, the data is presented on a website accessible to only specific users, as well as a more granulated version of the data is presented on an interactive Tableau dashboard. So to further demonstrate this device, I'll hand it off to Tobi and Chengxuan.
The WiseCam version 3 on the pedway between ECA and the Medical Sciences Building, pointed at 114th Street and 87th Avenue. It is wirelessly connected to the NVIDIA Jetson Nano, which is located in classroom down the hall in ECA. Conditions are good, but there are some branches in the way. Moving on to the brains of the project, the NVIDIA Jetson Nano is running both the detection and tracking algorithms and the client side of the RTSP video. Running these programs is quite intensive, so we added a fan for extra cooling to ensure that there is no thermal throttling. The video does suffer from stuttering as it has to do some image processing. However, this is not indicative of the performance of the algorithm. It is just meant to serve as a visual aid. That being said, the data is being fed into the database in batches, and for the purpose of this presentation, we set it to upload after every 20 process frames. As you can see, the data is being sent to the database in real time, and it is uploaded to our website's endpoint, which you have chosen to visualize for easy understanding. There are 4 main parts to the project: the camera, which is the WiseCam version 3, the computer, which is the NVIDIA Jetson Nano, the database, hosted on Google Firebase, and the website. The code base, which is available on GitHub, is locally cloned on the Jetson Nano, which is the center of the entire project. The Jetson Nano is a small but powerful computer popularly used for entry-level AI applications. It was the best option to run machine learning models under our budget. The software is based around the use of object tracking and object detection. For object tracking, we use the observation-centric, simple, online, and real-time tracking, otherwise known as OXORT, which is a pure motion model-based multi-object tracker. It aims to improve tracking robustness in crowded scenes and when objects are in non-alien motion, which serves our purposes. As for object detection, we use YOLO, which stands for You Only Look Once, an algorithm that uses neural networks to provide real-time object detection. This algorithm is popular because of the speed and accuracy.
Of course, in order to perform object detection and tracking, we need to provide a video feed for the software. We use the WiseCam V3 as it was provided the best price to performance ratio of the camera we tested. It was also chosen for its ability to support real-time stream protocol, RTSP, which transfers real-time data from multimedia device to an endpoint device by communicating directly with the server streaming the data. In other words, we were able to access the camera feed through our software at a secure URL. This means that the Jetson and camera could be connected wirelessly, allow for more freedom of placement. We were able to run the project with the camera at McEwen University and the Jetson Nano at the University of Alberta. For another major component of our project, we have to upload the connected data to a database, Google Firebase, for storage and future analysis. To do this, we added a script to wait for the program to process a specified number of frames before connecting the data and sending it to the database in batches. The reason for this being we wanted to reduce the amount of reads and writes to the database, as it could become costly, especially in times of high traffic. And other reason for using Firebase is that it was familiar, so we were able to easily fetch the data from database using the Firebase API and use it in our website.
So this is the sign-in page of our website. We created a simple website using React and the Google Maps API, as well as Firebase authentication to ensure that users with designated accounts are the only ones that can access our website. So once you sign in, you get to see a map with icons representing our active devices. So as of now, we only have one active prototype, so all the information you see here is just for demonstration purposes. But once you click on one of the cameras, you can see its most latest information with the different vehicle types within that hour. Clicking the other camera shows you its information. So we further visualize this data using Tableau, so I'll hand it over to Rucha.
The collected data is presented in an interactive Tableau dashboard. The interactive feature will support the Tomorrow Foundation in extracting business insights to support their future policies. This is the dashboard. Currently, the dashboard is built on static dummy data because we were not able to integrate the tool with our live database. Theoretically, the dashboard will be updated as the database is updated. There are currently 3 sections. A geographic map, which displays a pie chart marker that indicates the location of each device, and the latest vehicle count and distribution. There is an enlarged pie chart that provides the breakdown and total vehicles detected in each of the different coordinates. And the final section is the display of the data in a traditional table format. The slider at the top represents the timestamp for the data being displayed. It can be moved to show the data collected at various times throughout the device's active lifetime.
Here are some of the things that worked for us in this project. The detection and tracking algorithms worked with high accuracy. The website was able to pull data from the database consistently and securely. The camera stream was steady with few disruptions in service. The data visualization in Tableau, and the project can be run with just 2 lines after the initial setup. So it's quite easy to use and run.
What didn't work? Despite the NVIDIA Jetson Nano was able to run the YOLO framework and produce high accuracy results, it wasn't powerful enough to run the framework fast and efficiently. We were unable to detect when the camera had been moved out of position because of the hardware performance issues. Some features and functionality were disabled such that the NVIDIA Jetson Nano could not recognize the camera was out of position. We didn't implement setup script to install all the software requirement automatically, as well as preparing a snapshot for the system to avoid time-consuming setup process for each new unit.
Although the device works successfully, there are areas of improvement for this project. Firstly, integrating the Tableau dashboard into the website to make the website a one-stop shop for the Tomorrow Foundation, able to access the data in various formats. This goes hand in hand with conducting further testing and fine-tuning of the website. Next would be to explore the possibility of using a single high-specification machine that can run multiple instances of the software for different cameras. This can be understood similar to a hub model. This goes along with utilizing a Jetson board with pre-assembled and pre-installed versions of the Jetson to minimize setup time for developers. Alternatively, using a standardized disk image would also support the project's scalability. To improve user experience, implement a mechanism to alert or notify the user when the device has moved out of position or has poor visibility. And the final major area of improvement is to migrate the database and web hosting to Microsoft Azure, as they waive up to $10,000 in charges for charitable organizations.
In conclusion, the overall goal of this project was to create an easy to maintain and use traffic counter that collects and stores traffic data. We were able to successfully achieve this goal as we created an accurate, low-cost traffic counter that is easy to install and maintain by users with no prior technical background. The traffic counter was able to identify and track different vehicles as well as upload that data to the cloud. Furthermore, we developed a website that was able to visualize the data collected by different traffic counters, as well as develop the more granulated version of the data using an interactive Tableau dashboard. Lastly, we'd like to thank Sandra from the Tomorrow Foundation for giving us the opportunity to work on such a meaningful project, as well as Dr. Knudsen, Eric, and Wentao for their help and guidance throughout the semester. Thank you for listening.